In this next question, this is a very, very popular question that I've seen come up quite a bit. It says, find the value of the constant k that will make the function continuous. And usually they'll just say that, but you need to know that we really care about at the location of the rule change, because when the rule changes, that's when we could have discontinuity. So every time you're asked to find the value of the constant k that will make the function continuous, we're looking specifically at where the rule changes. And anytime you see the word continuous, you should be thinking about the definition of continuity, which has 3 parts. Again, part 1 is about the limit, part 2 is about evaluating the function at that value, and part 3 is that 1 and 2 agree. So if we look at 7a, we're finding the value of k so that the function is continuous, all right? So in order to find k, I need an equation, and the equation is going to come from part 3 of the rule. Part 3 says that the limit is equal to the function value. So the limit as x approaches 1 in this case has to be equal to f of 1. So we need to find those things. We need to find the limit as x approaches 1, and we need to find f of 1. And it's pretty easy to find f of 1 because I'm going to plug it right in here. This is x is less than or equal to 1. So f of 1 is equal to 3 times 1 plus 2, also known as 5. All right, so f of 1 is 5. That means in order to be continuous, this must equal 5. In order to be continuous, f of 1 is 5, so the limit as x approaches 1 must equal 5. The limit as x approaches 1 from the left is 5, because we already did that, 3 times 1 plus 2. The limit as x approaches 1 from the right must also be 5. And there's k right there. So the limit as x approaches 1 from the right, since the limit has to exist in order for it to be continuous, limit as x approaches 1 from the right must be 5. Therefore, 2k minus 1 must equal 5. Because when you're doing the limit as x approaches 1 from the right, you're plugging 1 in for x, but we know that that's supposed to be 5. So 2k is equal to 6, and k is 3. So when k is 3, this is continuous. You can plug 3 back in and check that the limit as x approaches 1 is 5, that f of 1 is 5, and that all of it still works nicely. If we look at the next one, we have to check that the limit as x approaches 2, or we have to force, I'm sorry, not check, we need to force the limit as x approaches 2 to equal f of 2, because we want it to be continuous, and we want to find the value of k that will make it so. So if we find f of 2 right there, because x is less than or equal to 2, f of 2 is equal to 4k, which means that limit as x approaches 2 from the left and the limit as x approaches 2 from the right both need to make 4k. So let's do that. Let's do the limit as x approaches 2 from the left. We already did that one. That's 4k. That's 4k. All right, and the limit as x approaches 2 from the right has to be 2k minus 6. These have to be equal. They have to be equal. Because in order to be continuous, the limit as x approaches 2 has to equal f of 2, and the left and the right have to agree. So these also have to be equal. Hello. So let's set them equal to each other to find that k is equal to -3. And when k is -3, the function is continuous. So I'd like you to try C on your own, and then check your answer in the binder. Because now we're moving on to our conversation about differentiability. Okay, so to recap, again, the definition of continuity is of a function. A function is continuous when a function is continuous at c when the limit as x approaches c exists, when f of c exists, and most importantly, when the limit is equal to the value of the function. So the limit as x approaches c is equal to f of c. There's our continuity. So now we're going to talk about differentiability. All right, so to read this together in calculus, we are interested in examining whether functions are differentiable. In simple terms, a function that is differentiable is smooth. A differentiable curve will have no sharp points, or points whether the tangent line to the curve is vertical. So there are no sharp points and no points where the tangent line to the curve is vertical. Okay? And you can read the roller coaster example on your own. So here are some definitions for differentiability. Differentiability at a point, at a specific point. A function is differentiable at x equals c if and only if the derivative exists when you plug in c. So f prime of c must exist in order for the function to be differentiable at a point. Now differentiable on an interval. So from like x equals this to x equals that. A function is differentiable on an interval from a to b if and only if f prime of c exists for every value of c in that interval, for every value inside that interval from x equals a to x equals b. For every value, you can plug in an x value inside this interval into the derivative and it works, it exists. That's how you're differentiable on an interval. And now a differentiable function. A function is differentiable if and only if f prime of c exists for every value of x equals c in its domain. For example, polynomials, sine and cosine, and exponential functions are differentiable functions. We start to have issues when we're looking at the roots and absolute values, but your polynomial functions, your sine and cosine functions, and your exponential functions are differentiable. This is important. Also important is the connection between differentiability and continuity. Since a function that is differentiable at x equals c is smooth, that implies that it must also be continuous at x equals c. If it's differentiable at x equals c, then it is continuous at x equals c, which gives you this very important statement. Differentiability implies continuity, but continuity does not imply differentiability. A function could be continuous and not differentiable. But if it is differentiable, then it's automatically continuous. Super important. Differentiability implies continuity, but continuity does not imply differentiability. If a function is differentiable at x equals c, then it must be continuous at x equals c. If a function is continuous at x equals c, then it's not necessarily differentiable. It can be, or it cannot be at x equals c. If a function is not continuous at x equals c, then it cannot be continuous. It cannot be differentiable at x equals c. So differentiability implies continuity, and then I believe it's the converse of that. If you're not continuous, then you're not differentiable. So if you know for a fact that it's not continuous, then it for sure cannot be differentiable. All right? If it's not continuous, then it's not differentiable. I hope that that makes sense. You may want to rewind that and hear that again, but this is really important here. All right, really important here. And when two curves meet at a sharp point, we've kind of talked about this, but when two curves meet at a sharp point, that's called a cusp point. Functions that have cusp points have vertical tangent lines right there. So therefore, they're not differentiable at that point. Then we also have corners. Functions that have corners have no tangent lines. You can't put a tangent line on a corner. Therefore, also not differentiable at that point. Now on this last page, we are kind of doing what we did in the other examples where we're finding the value of k such that the piecewise function will be continuous. Here we wish to determine, and we're going to do that value of k thing later, but anyway, we wish to determine if piecewise functions are differentiable. So now we're looking at piecewise functions, and we're looking to see if they're differentiable. So it is possible and usual that both pieces of a piecewise function are differentiable, that both pieces of the piecewise function are differentiable. I'm not seeing my, all right, there we go. That both pieces of the piecewise function are differentiable, but we really care with piecewises piecewise functions where the rule changes. So again, we're in a piecewise, we will care about where that rule changes. So we want to check continuity at that x value, because if the function is not continuous there, then it cannot be differentiable there. If it is continuous, we then need to check on differentiability, okay? So let's do a continuity check on this guy right here. So we want to check that the limit as x approaches 2 equals f of 2. All right, f of 2 right here is what? Is 4 minus 6 plus 10. Is f of 2, 4 minus 12 plus 10. So f of 2 is 2, and the limit as x approaches 2 is also going to be 2. And if you do that test for continuity, you'll see that f of x is continuous at x equals 2. Okay, it is continuous at x equals 2. Now we got to check differentiability. So to check differentiability, we're going to apply the same rules, but to the derivative. Because differentiability means that the derivative is smooth and continuous, that you can draw the graph of the derivative without lifting your pencil. Therefore, we have the same criteria, except on the derivative. So to check a piecewise for differentiability, we're checking that the limit as x approaches c of the derivative exists. We're checking that f prime at c exists, and that those two values are the same. So we've determined that this is continuous. Now let's take the derivative to determine if it's differentiable. So the derivative is 2x minus 6 for x is smaller than or equal to 2, and negative 1 for x is larger than 2. The limit as x approaches the derivative, as x approaches 2 from the left on the derivative is negative 2. And as x approaches 2 from the right on the derivative is negative 1. And since those disagree, we have not differentiable. So this function is continuous, but not differentiable. And now you will take a quick second to graph that, and you will find a corner. When you graph this, you will find a corner where this function and this function meet each other because it is continuous, and you'll find a corner. Remember, you can be continuous, like this little birdie graph, but that cusp, or in the case of this graph, that corner, or it's actually going to be a cuspy corner, looks like, from my drawing here. You got a little cuspy corner, implies not differentiable, okay? I'd like you to try B, C, and D, and I'll give you answers so that you can kind of work your way through that. This one is continuous and differentiable. C is neither continuous or differentiable, so nor differentiable, it's neither of the two, so it's not continuous and it's not differentiable. And D is continuous and differentiable. So try them and be prepared to ask questions on any that you attempted and did not get these answers on. And I'll do 9A so that you can then do 9B and we'll be done. So find the values of A and B that make the function differentiable. Find the values of A and B that make the function differentiable. Since I have two unknowns, I need two equations. And any question like 9 is going to require you to take a look at the continuity and the differentiability. If the function is differentiable, and we're going to force it to be because we're finding values so that the function is differentiable, if it's differentiable, it's continuous, okay? So equation 1 is going to come from the fact that we need to force it to be continuous, and equation 2 is going to come from the fact that we need to force it to be differentiable. So in order to be continuous, and we care about where the rule changes, the limit as x approaches 1 has to equal f of 1. All right? F of 1 is 1 times a plus 1. So f of 1 is a plus 1. And the limit as x approaches 1, well, from the left is going to give you a plus 1, and from the right is going to give you b minus 3. And these have to be the same, because f of 1 has to equal the limit as x approaches 1, and the limit as x approaches 1 has to be the same on the left as it is on the right. So now we have one equation. b minus 3 equals a plus 1. I can't solve for that because I have two unknowns. So I need another equation, and that's going to come from looking at differentiability. In differentiability, the limit as x approaches 1 of the derivative has to equal f prime of 1. So let's take the derivative. I'll do that down here. The derivative is 2ax when x is smaller than or equal to 1, and b when x is greater than 1. So f prime at 1 will be found by looking at this line. F prime of 1 is 2a. And the limit as x approaches 1 of the derivative is on the left is 2a and on the right is b. And these have to be the same, so 2a must equal b. Now I have two equations that are true, so it's easy to solve by substitution. Oh, not right there. Sorry about that. A is b over 2, right there. So we can plug b over 2 right in there, or we can plug 2a. Actually, I don't know why I did all that, guys, because, oops, a was already isolated. B is equal to 2a. Why don't we just put that guy right in there? Come on, Ms. B. So 2a minus 3 equals a plus 1. To find, do the algebra to find that a is 4 and b is 8. So use that as a guideline for this question where the answer is a equals 9/14 and b equals negative 27 over 7. So that is the video on continuity and differentiability. We will go over any questions you have tomorrow. This is a very, very important concept, comes up quite a bit, of course, and we'll have a work day on this tomorrow. Yeah, this is Miss B signing out. See ya, bye.